Assalamualaikum warahmatullahi wabarakatuh. We are from Group 2. Our group members is Nuridin Aisyah, Nuridin Azwani, Walana Suha, and Amiratul Farhana. So, our group will be presenting on assignment 2, which focus on the critical engineering task of locating the LZ fault for underground power cables. So, we will guide you through the modern and traditional methods that is used to pinpoint these hidden electrical issues. We will proceed with our presentation agenda. To give you an overview of our presentation flow, we will start with a brief introduction to the types of underground faults and the difficulties that is faced when trying to locate them. Following that, we will take a deep dive into our two assigned technique, which is the popular Murray loop test and time domain reflectometry, before wrapping up with our conclusion and reference.
Moving on to our first topic, let's take a look at introduction to underground cable fault. When we talk about underground power distribution, these cables are typically placed securely in the deep trenches or protective ducts. Because they are buried and shielded from weather, wildlife, and traffic, they actually have a relatively low fault probability compared to the overhead lines. However, when a failure does happen, it generally falls into one of three common categories. First, we have an open circuit fault. This occurs when there is a literal break or snap-in the core conductor itself. Because of the part is completely broken, the electrical resistance spikes into infinity ohms. On the diagram, you can see this represented by that physical gap in the internal wire core. Second, short circuit fault. This happens when the protective insulation surrounding the internal wire fails, causing two separate wire conductors to make direct metal-to-metal contact. This creates a path of zero resistance between them. In the illustration, you can see the insulation breakdown where the two cores touch. Third and lastly, we have an earth fault. This is when a conductor breaks past its insulation layers, but instead of touching another wire, it makes direct physical contact with either the outer metal sheets or the ground itself. Like the short circuit, this also drops the resistance to 0 ohms as the current leads directly into the earth. This brings us to the core difficulty. On the left side of the slide, you can see what we call fault identification. And the good news is that this part is relatively easy. Using a portable mega instrument, technicians can safely, quickly, and accurately identify the exact type of fault we are dealing with. By conducting rapid insulation resistance testing, the meter immediately flags whether we have an open circuit, a short, or an earth fault based on those infinity or 0 ohm readings. But knowing where the fault doesn't tell us where it is. This brings us to the right side of the slide. Fault localization, which is incredibly hard. Pinpointing the precise physical meter mark along kilometer of burying line is a massive engineering challenge. Unlike overhead lines where you can drive by and visually spot a downed wire or a broken insulator, underground infrastructure is entirely hidden from the view. As you can see in the cross-section diagram, these cables are buried beneath deep, heavy layers of roads, city concrete, and a maze of other underground utilities and draw-in ducts. These massive structural barriers severely limit our ability to perform visual inspection, or could be in case. We can't just dig up an entire city street guessing where the break is. We have to know exactly where to strike before shaft hit the ground.
I will be presenting the first method assigned to our group, the Murray loop test, which is traditionally one of the most popular techniques for locating cable faults. This method operates on the principle of a wet sandwich circuit. To set up this test, as illustrated in our connection layout, we connect the faulty cable to a completely healthy, parallel sound cable running beside it. At the far end of the line, these two cables are securely joined using a very low resistance shorting strap to complete the loop circuit. In terms of its operating principle, two highly accurate variable resistors R1 and R2, a DC power source and a sensitive galvanometer are hooked up at our testing station. As shown in the circuit schematic, the resistors are adjusted manually until the galvanometer reaches zero current, meaning the bridge is perfectly balanced. Once balanced, the loop resistance corresponds directly to physical distance. Using this exact bridge formula, D equals R2 over R1 plus R2 multiplied by 2L. We can calculate the exact distance from the test station straight to the fault location. Looking at the practical advantage and disadvantage, the primary benefit of the Murray loop test is its long-standing accuracy and simple circuitry when dealing with standard earth and short-circuit issues. It is also entirely unaffected by the resistance at the fault point itself. However, its major drawback is that it strictly requires a completely healthy parallel return wire. If a catastrophic event damage all cables in the trench at the same time, this test cannot run. Additionally, it fails completely for open circuit fault where the loop is physically broken.
Moving on to our alternative method, time domain reflectometry or TDR. The fundamental concept behind this method is that it is often called electrical radar. As you can see in our connection diagram, TDR offers massive connection layout advantages over traditional bridge methods. First, it utilizes single-end diagnostics, meaning the TDR unit plugs directly into only one accessible cable terminal end. Second, there is no loop required, giving us zero reliance on parallel companion wire, some cables or returning circuits. And third, we leave an untouched far end, meaning the far end of the cable requires zero physical shorting jumpers, grounding straps or manual modifications. This makes it incredibly easy to deploy in the field. Okay, now let's dive into the operative principle and the math behind it. TDR calculates distance using the equation D equals to V multiplied with T over 2. To break down what this means, V is the velocity of propagation of electricity through the insulation medium. T represents the total round trip elapsed time delay of the reflection wave measured right up to the signal's rise time. And D is our resulting physical distance to the impedance anomaly. If we look at the graph, we can see exactly how the TDR unit reaches the cable. The solid black line represents our reference square wave being sent down to the line. If the wave encounters an open condition, represented by the blue dashed line, the signal steps sharply outward, indicating an open circuit break. However, if it hits a short condition, shown by the red dot line, the voltage drops drastically downward. This allows us to instantly know the exact type and location of the fault. Finally, let's evaluate the advantages versus disadvantages of time domain reflectometry. On the left, our core advantages are that TDR easily calculates the location of open circuit faults where bridge loop fail completely. It also provides real-time visual graphical signatures of the cable condition directly on the display screen. Because it is fully standalone, it does not need any extra routing lines. However, looking at the right side, our disadvantages are that a TDR unit is significantly expensive, high-tech digital computing instrument. It also demands expert field interpretation to read and analyze complex wave graphics cleanly. Lastly, it struggles to notice high resistance, intermittent arcing faults that only spark under high active distribution voltages. Okay, so now I will hand the presentation back to Dina to conclude our topic.
Conclusion is, locating the exact fault in underground cables is very important because it helps to reduce excavation costs, repair time, and power outage, while tools such as the Megger are useful for identifying the type of cable fault. Additional methods are required to determine the exact fault location. Also, the Murray loop test is a reliable and cost-effective method for locating earth and short-circuit faults when a healthy parallel cable is available. However, it has limitations and cannot be used for open circuit faults. On the other hand, time domain reflectometry is a more advanced technique that can accurately locate faults from only one end of the cable without requiring a parallel core. Because of its accuracy, speed, and ease of use, TDR has become the preferred method in modern underground cable fault detection. That's all from us. Thank you.